Yeah, so, but we actually got some good stuff, but it's been a while.
Okay, well, I would like to welcome everybody and thank everyone for coming to this Wrigley sponsored with the Environmental Studies Program Sustainability Professional Development Speaker Series. It's a lot of words, we were just joking about that. It's a really fun seminar, even though I can't remember the actual name for it, where we get to hear stuff from people who are out in the real world doing the work that I think many of you want to go on to do. And take the advantage of this time afterwards to talk to them about how they got there. What did they do to actually get into these kind of positions? This one's also particularly interesting to me because we have sort of an entrepreneurial twist on it, which is something else that we've been really trying to work at within the Wrigley Institute, is getting more interest in entrepreneurial solutions and we believe that a lot of those solutions are coming from you guys and all of your bright ideas. And this is my shameless pitch to point out that we do have the Wrigley Prize in Sustainability next semester. And so, if you have ideas of sustainable entrepreneurial ideas, come to us, let us know, and we'll help you learn how to do a pitch and potentially win a couple of $1,000s. So let us know if you have any of those kind of ideas. But I don't want to take up any of our speakers' time, so I'm going to actually turn it over to Dr. Ken Nielsen to introduce our speaker.
I thank you all for coming too. I had the honor of speaking to this class of Diane's last week. And I told them they all had to come here or they would be failing grades. So, anyway, it's a great pleasure for me to introduce Orianna Bretschger. Probably about 2002, I gave a lecture over in the engineering school. 2004. She'll correct everything I say. And after that lecture, Orianna came and talked to me. She was an engineering student and wanted these ideas about electric bacteria to be turned into some kind of knowledge that would be useful for, as you're going to see today, for actually helping the environment. That took about 4 years of activity. 2008, I think you graduated. And and it's just been fantastic watching it. After she finished here at USC, she went to the Craig Venter Institute, where I happened to be on sabbatical at the time. So we got to keep working together. And even since her graduation, we probably published 5 or 6 papers together. So, and fantastic stuff. I can't wait to hear it. So I'll turn it over to Orianna.
Thank you. Thanks so much. Thank you so much, Ken. I have to say, I owe a lot to Dr. Ken Nielsen. So when I first arrived to USC, I was in the material science department, and I was working in Dr. Nutt's lab, and Dr. Nutt is wonderful, anybody who knows him. But I was breaking apart epoxy-embedded carbon fiber rods all day long. That was what I was doing all day long. It was pretty miserable. And when I went to Ken's talk, I was just blown away by this possibility of bacteria being able to breathe rocks and produce electricity. And I had never taken a biology class ever. And somehow I managed to convince him to take me into his lab. And that really catalyzed everything that I'm doing today. And through our collaborations over time, I have to say Aquacycl is owed to Ken Nielsen. So thank you, Ken, and thanks for having me back. So I'm going to take you through a bit of a journey today. So first off, what is Aquacycl? What are we providing? There'll be a little bit of science in there, not much. And then I'm going to take you through really what my startup journey has been like. So Aquacycl, we're headquartered in San Diego. We offer the bioelectrochemical treatment technology, or BET, and our goal is to make wastewater treatment better. So I did not start off as an entrepreneur. In fact, I didn't start off, well, I just told you I didn't start off in biology. But what has been the continuing theme throughout my career has been electrons. So I started off undergrad at Northern Arizona University. I did my Bachelor's of Science in Physics and Astronomy, so all electrons, right? Then I got a job. I designed guidance systems for missiles, and that's electrons for missile guidance. So it was the first use of CCD cameras, actually, in the Tactical Tomahawk guidance system. Then I decided I didn't want to make bombs for the rest of my life, and I came to Southern California specifically for graduate school, and I met Dr. Nielsen, and I also met Schuonella onidensis MR1. I'm sure many of you here have as well. And so this is all about electrons and Schuonella, from 2004 to 2008. And as I moved to the Craig Venter Institute, it was, okay, how about electrons in communities of organisms? How do these guys electronically communicate together and to their environment? And then how can we control that very specifically for the function that we want to have happen, which is wastewater treatment? And then ultimately, through the work at Venter and here, we, in parallel paths, understood enough of the fundamental biology and started to develop a technology around that. And that has now led to where we are today with Aquacycl. And so now it's all about wastewater and how do we move electrons around to optimize wastewater treatment. So a little bit more about the company. So we're California registered, woman-owned business, headquartered in San Diego. We have R&D and manufacturing in San Diego, Tijuana, and South Korea. We've been validating the technology across multiple different types of waste streams, but we've really narrowed in on the food and beverage sector as the first product fit for what we're doing. We have active installations in many places, 2 in Southern California. We've got a unit in Tijuana. We just shipped out a unit to Tennessee, and we have an operational unit on Oahu for the military as well. So this is not done in a bubble by any means. So the leadership team at Aquacycl is myself and my partners Sophia and Ryoji. All of us have worked together for many years, mostly through the course at JCVI. But we've brought on board members that have that entrepreneurial, spirit and have had entrepreneurial success to guide us scientists through the slog of startup world, as well as help us, with the critical points of building a business. And so that's true, from the water industry side as well as on the finance side. And, one of the things anybody who's considering entrepreneurship, I knew nothing when I formed Aquacycl, absolutely nothing about how to do this. But one of the, really critical things that helped us really get to where we are today is accelerator programs. And so depending on what you're interested in doing, there are multitudes of accelerators out there to help catalyze your business. Imagine H2O is probably one of the best known and most respected in the water space. We went through that accelerator program in 2018. Which was really amazing for us. And we're still a part of other accelerator programs based in San Diego, making those connections to potential customers, investors, helping refine the pitch. All of these opportunities are out there. There are many of them. So take advantage, and I know they're here at USC as well. So why do we care about wastewater? Well, wastewater treatment really is a global problem. 80% of wastewater that is generated worldwide is discharged directly to the environment, either with minimal treatment or no treatment at all. And as you can imagine, this has really devastating consequences on human and environmental health. Now, the reason that this is the case is not because there aren't wastewater treatment technologies, right? These technologies have been around for decades. I mean, the Romans had bathhouses and sanitation, right? But the problem is that the infrastructure that we enjoy today for the population in high-income countries is just not practical in many other parts of the world, right? So while those technologies exist, they are extremely infrastructure intensive, require a lot of energy to run, and highly skilled operators in most cases. And these are the big centralized plants that we know and love here in Los Angeles. If anybody's taken a tour of Hyperion, yeah, it's awesome, right? It's pretty amazing. it's really incredible, you know, that you have 300 million gallons of wastewater being treated per day just at that one single plant, right? And that really is public health 101. I mean, that's sanitation. That is what is enabling our society. And so without it, you know, you have what happens to the rest of the world, or, you know, 2.6 billion people who doesn't have access to a toilet. And so more people actually have a cell phone than a toilet. This is a true statement. So our goal, our mission has always been sanitation for all in Aquacycl. But in order to get to that goal, we have to make money, right? And keep ourselves sustainable so we can make the cost of our product accessible to areas that need it the most. So we narrowed in on food and beverage as the specific product market fit, right? And specifically with microbial fuel cells or bioelectrochemical technologies, we do really well in a niche that is unfilled, which is very high strength organic wastewater and very small volumes. So you're never going to see a bioelectrochemical system at Hyperion treating 300 million gallons a day. I mean, I hope I can eat my words, but I believe that this is not going to be the case. But what we do really well is distributed treatment, on-site treatment for point source remediation. So what I mean specifically by high strength, okay, what's in a city sewer, chemical oxygen demand is COD. It's a measure of total carbon, right, that total organic carbon. In a city sewer, you will see levels between 300 and 400 milligrams per liter of COD, okay? Now, this is 300 times more concentrated than what you would see in a city sewer. Most of it is just sugar, right? It's highly concentrated sugar coming out of the production of soft drinks, beer, wine, you name it. But these waste streams also come out at smaller volumes. And so we can treat up to 150,000 gallons a day with the current technology scale that we've got. And potentially we can get a little bit bigger. But the value proposition doesn't exist for the customer as well. We'll talk a little bit what that means. So the niche for us is really high strength wastewater, right, at small volumes. And just to put this all in perspective, like how much of this really exists, right? So every gallon of beer generates 4 to 6 gallons of wastewater. Every barrel of wine generates 5 barrels of wastewater. Every packet of M&Ms generates 2 to 3 gallons of wastewater, right? So these are significant flows. And it can cost each facility, whether you're Nestle or Mars or Coca-Cola, it can cost per facility about $1 million a year to deal with these small flows, small, highly concentrated flows, right? So the alternative to Aquacycl is holding and hauling. So that means you capture this waste, you put it in a calamity tank, and you pay a third party to haul it off site, and it's typically discharged to a landfill, in some cases to private land. Right? And in that case of private land, just think about what's happening to that soil, right, over time. So it becomes another ecological issue and certainly doesn't help anybody's sustainability story, right? So the other option to hold and haul is conventional anaerobic digestion, also a biological process where you've got methanogens that are fixing CO2 into methane. And this has been a technology developed, you know, it's been in use for 35 years, and it works pretty well. But it does not work well in production environments where you may be closed for a weekend. Where your concentrations are going to vary significantly throughout the day when you're changing a product line, or when you have variations in temperature of what you're producing. So any fluctuations in pH, mixing, temperature, concentration, and volume can really throw off a methane digester, meaning it either doesn't make any methane, or it creates such a toxicity event you have to dump the whole batch. And these anaerobic digesters typically take anywhere from 15 to 40 days, right, to address wastewaters of this concentration. So it's a long residence time. And if you have a toxicity event, you're hauling it away anyway, right? So it becomes a problem. And if you're not making any methane, for a lot of our food and beverage customers, right, they've invested in these anaerobic digesters since it's a proven technology. But even for this scale, 150,000 gallons a day, it may cost around $10 million capital expenditure just to get the equipment installed. Then it's $500,000 a year to operate on site. These are significant investments, and if you're not getting methane back that you can use in the process of cogeneration to make electricity and heat, right, then there is no return on that investment. So a lot of the food and beverage customers that we've talked to who have purchased anaerobic digestion and the service that goes with it are fed up, and most of those sites that we visited, they're not working. So here we come to the rescue. So our system is actually, our service model is fully rental equipment. So we're not selling the customer any equipment. We don't expect them to operate this. They're not going to know how. It's not their core competency. They don't want to run it, right? So we offer treatment as a service. So the equipment comes in, we provide guaranteed performance for all of our customers, and we do provide some energy neutrality in the operation. We can recover energy as DC power, a little, right? And we can trickle charge a battery pack and run our pumps and data management systems off of that battery pack. And we've demonstrated that with the military pretty successfully. But all of this will lead to immediate savings for the customer, right? So wastewater treatment is really energy intensive, and anaerobic digestion is the only thing that really will pay back in energy. So if it's not working, you're going to be paying $2 million a year in operational energy costs to run an aerobic process for something this size, right? So this is our business model. We found our core customers, and what we offer is a modular plug-and-play system, right, which fits in, ties in directly to either existing tanks, or we bring in our own tanks. We always require a degridding step, so this is removing bottle caps and rocks and strange things that accumulate in the production floor, any of the inorganics. Then it goes to an equalization tank, so the blue tanks that you might see there. We do a sulfur removal step. Now this is a biological step that we've integrated now for any high protein wastewaters. So we've noted that bioelectrochemical systems, our BET systems, are really good at getting rid of sulfide, but then everything else slows down, right? All of the rest of the reactions slow down. So we need to get rid of total sulfur, because even sulfate, as it gets into the system, which is anaerobic, will ultimately be reduced to sulfide and then absorbed. So what we do is we embed what we call a micro-aeration unit in the equalization tanks. We create an environment where we enrich for sulfur oxidizers in a biofilm, and those sulfur oxidizers capture the sulfide before it moves into our reactors. And then as a part of our service, we remove that biofilm annually and restart it again. So that helps actually keep total sulfur going into the system below 5 parts per million. So after that sulfur removal step, which is really only required for high protein waste streams, goes into our reactors, which are inside that 20-foot by 8-foot shipping container. We have a 40-foot model as well. We remove anywhere from 90% to 99% of the total organics, and then we can discharge to sewer or to another post-treatment system to elevate that level of reuse for the customer on site. All right, so you're hearing my pitch. This is the, it's a proven technology. We've been demonstrating this in the field in real-world applications at scale for the last 4 years. We do better with higher concentrations of waste, and I'll show you a little bit of data to that later. We can, in some situations, offer energy neutrality, but it really depends on the type of wastewater we're treating and the concentration we're starting with, right? Because that carbon concentration is the chemical energy content. We can only, at theoretical best, convert that 30% of that chemical energy into DC power, right? In practice, it's much closer to 10%. So if we've got more chemical energy to convert, right, we get more electricity and power that we can use. But the real goal for us is accelerated removal of carbon. We can also deal with suspended solids. So TSS is total suspended solids. So this is the goop, this is the sludge, this is stuff that also becomes really problematic in other wastewater treatment technologies. We can handle up to 3,000 parts per million. Every other tech is about 300 parts per million, right? And we reduce that solid load coming in by about 80% within the residence time of the system. We've demonstrated that at a pig farm over the last 4 years. That's a lot of fun. And so all of this really relates to being able to have a small footprint, a very efficient system, and the fact that it is a biofilm system, right? It's a fixed film. You're not flushing out your bacteria every time you bring in new wastewater. Allows this system to be very robust relative to other technologies as well. So these toxicity events I talked about a little bit earlier, basically you're killing your bugs, right? In any biological system, if you have a toxicity event, bugs are just toast. So you have to regrow your whole community of organisms, which can take anywhere from 3 weeks to 3 months, right? Or longer in some cases if we're talking about anaerobic digestion. With a fixed film, right, we can actually drain these units, and we've done this. We've taken operational reactors, drained out the liquid, put them in the sun, and the material still holds some moisture, so it's not fully dry. Put them in the sun for 2 months, and then we pop them back into that treatment train, and we actually see recovery within 24 hours of both electrochemical signal as well as COD removal. We can run bleach through them. We've electroshocked them. We've done some terrible things to these biofilms, but they do come back usually within 48 hours. So of course, in clinical situations, that's why biofilms are so terrible, right? The only way to get rid of them is truly mechanical destruction. It's great for us in wastewater treatment, and this helps in a production environment quite a bit. All right, so the science behind it, you all may be familiar with this already, but I'll just run through it. So this is a microbial fuel cell, right? And our product is based on a microbial fuel cell. And we're using naturally existing bacteria already present in the wastewater that we're treating. So we do a fresh enrichment with every customer. We're not bringing anything grown in the lab. We're not providing anything that's been engineered. What we do is we create a redox environment specifically to select for those microbes that have the capacity for extracellular respiration, right? So as these microbes come into the system, they start to see all of the conductive surfaces that we have there, and they start using those surfaces as a way to respire, as a way to breathe, right? So as they form that biofilm on that surface, they are discharging electrons to that surface through their process of respiration. We can capture those electrons, we move them across a circuit, producing DC power. We have a gas diffusion electrode as a cathode, right? So oxygen naturally occurring in air, so there's no pure oxygen, there's no forced air, it's just natural diffusion. Comes across the barrier, and that oxygen is then reduced with electrons coming across the circuit and the protons that are dissolved in solution to ultimately make hydrogen peroxide, and in some cases, in the 4-electron reaction, new molecular water. And all of that comes out in a bulk, right? So we use a single chamber system with passive mixing to actually create these proton movement. And so we don't have to have a membrane. That gets rid of a lot of cost and maintenance. And the gas diffusion electrodes that we've created have been extremely reliable over the last 4 years that we've had them working in the field. The only times we've had to replace them is when squirrels get up there and start scratching away. We've had a couple birds peck in because we do keep them exposed outside for the durability test. But they haven't failed because they stopped working or we see a decrease in performance, which is great. So we got some patents and blah, blah, blah. So how the science really translates to a technology. So our units are literally the size of a car battery. They're small, right? So we can maintain the efficiencies that are required for a bioelectrochemical system. So wastewater will come in one side and moves past all of those vertical cylindrical surfaces that you see there, and the water and the sludge gets a little bit cleaner, right? COD, that carbon gets removed a little bit. And then what we do is we stack these things together like Legos to increase treatment quality or capacity. So we can fit 320 of our reactors in a standard 20-foot shipping container, 640 in a standard 40-foot container. And all of this is fully automated, so we have PLC controls and HMI interface, a web user interface for the customer, so that they can actually see performance of the system real time. Because what we're doing is we are monitoring the voltage off of every single reactor that we've got in place, right? And we know now that if voltage falls below a given threshold for the application, that there could be a problem. So we have algorithms to basically troubleshoot this for us and then bring up an alert to say, hey, we see that reactor number 212 is 20% below where it's supposed to be. We can actually troubleshoot remotely, figure out if there's a problem at the anode or the cathode. Then we can call boots on the ground, somebody that's at the site, to say, hey, reactor 212 needs the left cathode replaced. Right? So all of these things are racked up essentially on server racks. So then the service operator comes by, bypasses that rack of reactors, the rest of the system stays running, and then you replace that left cathode. And it's just like replacing a license plate, right? If you have to change out a battery, it's like changing out a battery in your car. We tried to keep it very simple, right? And because we are remotely monitoring, because we are training the folks that are going to be interacting with the system, if we're not the ones doing it, we can provide this guaranteed performance, right? And that's part of the service. So I mentioned before that the concentration and composition really impacts performance in each of these reactors. This is very true. So this is the only data slide you're going to get, so sorry. But this is basically how it breaks down, right? So if we have an initial chemical oxygen demand load in the tens of thousands, we're going to see much higher specific COD removal per reactor per day. And that's been a trend pretty much in everything that we've tested. Now, the outlier that you might notice here is soft drinks. That's because we had some pH issues. Coca-Cola, of course, is a pH of 2, right? So, once we redid this test, actually, and kept a good buffering system running, then we started to see much higher levels, so closer to the 2,000 milligrams per liter per day removed per reactor. These numbers, that specific removal rate, tells us how many reactors we need to get rid of a certain amount of carbon, right? So when we start talking to a customer, we need to know what's the volume that they're treating, how dirty is the water, how clean do we need to get it, right? And then knowing that and this information, we can figure out how many reactors it takes and then how many containers do they need to actually accomplish that goal. And so I'm showing you the data slide up here is showing you really exemplary COD removal in a batch condition. So almost all of our, all of our installations are continuous flow. So we flow at about 4 liters a minute, right? It's pretty slow relative to most flows. But what we see is that continuous flow actually will increase our performance anywhere from 3 to 10 times versus batch. So those of you in microbiology, you know why. Because when you're in batch and you are taking a very complex molecule and breaking it down into secondary metabolites, right? Those secondary metabolites can slow down the primary process. Right? You could be building up acids, right? That's going to slow down your fermentation. If those acids don't go away, right, that everything slows down. So in batch, that's what we see happen, right? So you see a majority of COD removal happens in the first 24 to 48 hours, and then it tapers off. And that's because you start to see those volatile fatty acids build up in the process, because we're just recycling the same batch of water, right? When we're in continuous flow, then each reactor, right, is used to seeing a different volatile fatty acid profile, or COD load. And that continuous flow is optimized to remove that particular, that consortia is then enriched specifically to address that flow, right? So that VFA load or that carbon, COD. So that's why we always see better performance in continuous flow. It's really difficult to do continuous flow tests in a lab with a 3-gallon reactor. You need a lot of waste sitting there. And while the waste is sitting there, it's changing, right? So it becomes really challenging to do any of these validation steps in the lab. So all of the tests that we've done continuous flow have been on site with the customer, where we have a consistent flow of waste that's really reflective of what would be coming out of a production environment. And so there's always challenges with that too, but this gives us a lot more confidence in the data and the ability to work on site. So going back to how we differentiate, right? So Aquacycl BET reactors, you know, we're faster, we're better, we're cheaper, all those good things relative to any of the other technologies that are out there. You know, there is one other commercial company in the United States which did do a bioelectrochemical treatment technology launched in 2016, and that was Cambrian Innovation out of MIT, and they provided the EcoVolt reactor. But the goal of the EcoVolt was to make ultra-pure methane. So an 80-20 split between methane and CO2, with that methane being evolved at the cathode. Unfortunately, the EcoVolt did not do well. It's unfortunate for us because that's a monkey we carry on our back, right? Even though our system does work, we're consistently compared to the company that didn't. So we're gaining traction even though that's still the case. So I mentioned to you where we have equipment in the beginning of the talk, but we just wrapped up a project with another Nielsen lab graduate, Louis Su, who is out on Oahu now working with the Navy with SPAWAR. So we had a demonstration for them at Wheeler Air Force Base, treating sewage sludge on a flight line. Fully containerized system, fully off-grid, it was augmented with solar to run everything. Worked really well. It was actually the best power results we've ever gotten out of a demonstration. Whatever they're eating out there is working really well. We just disassembled that, just as you know, the nature of the grant. And then we've got equipment still at the swine farm in Escondido, just outside of San Diego. We've had a system running at Joshua Tree Brewery for the last year. This is the first brewer to open his doors outside of the north gate entrance of Joshua Tree National Park. This is a unsewered community, so everything north of the park there's no treatment system there. Everything is on septic. And so this brewer had to negotiate with the water basin to say, okay, what do I do here? Because they weren't going to let him discharge his brewery effluent into septic. That aquifer is particularly nitrogen impacted, right? And so then that's because of all the septic discharge. So they said, you have to purchase some sort of on-site treatment. So we were connected to him through an engineering firm in San Diego, and even with the scale that we're at now in production, we ended up being half the cost of what everybody else was quoting him for a small unit for his brewery. So we started a demo unit with him, basically taking his home brew effluent, all of the cleaning products, everything. He's not doing any grain or hop separation, so we're taking everything. The load is around 30,000 parts per million. And we've been running that over the year with good success, and then that translated into a sale. We do have a system in Tijuana as well. And we, Sunday, I'll be flying out to Cleveland, Tennessee, which is outside of Chattanooga, for a installation at a confectioner called Mars. To demonstrate our unit there, and ultimately, hopefully, we'll be able to work with them globally to address their sustainability goals. So that's super exciting. So whenever you're making a pitch to investors, this is the slide that they care about most, right? Which is what markets are you really addressing? So we talked about food and beverage and why we work there. It is a big niche for us. There's a lot of options. There's a lot of verticals that we can address. We already have contracts with the military. They are interested in this from a forward operating base perspective. It costs a lot of money and sometimes lives to take waste off-site and address it in country, right? Same is true for water delivery systems. So if we can provide a device which doesn't have a thermal signature, right? Everything else is incineration. This doesn't have a thermal signature, and can reduce the amount of contractor time or delivery time for water and wastewater removal. That's a big win for the military. So that's why we've been doing demos with them. That does represent a big market opportunity. Our longest running demonstrations are with pig manure, right? And while it is an area we want to get into, We didn't start there because most of these projects have to be subsidized and are regulatory driven. So California is the #1 dairy state, right? But most of these farmers are working on a 6% margin, which means, right, these lagoons are a really cheap way to get rid of their manure. However, the state of California passed a bill in 2016 requiring that all livestock and dairy producers reduce their methane emissions by 40% by 2030, right? However, there are no technologies that are really cost effective to help do this. And so the state is now setting aside dollars to try and validate new technologies to help, because anaerobic digestion has a 50% fail rate at farms. It's just too complicated to run. So we know that there's going to be a shift, and we hopefully will be able to be at a price point at that point in time to address this market. And then ultimately, right, where our heart started and where we ultimately want to go is emerging markets, commercial buildings, residential homes. This represents the biggest market opportunity, but also the biggest need globally, right? So we'll get there, but that is our trajectory. And we are in talks, whether they are advanced or we're close to signing a contract with all of the names that you see here. And that's because all of them face these challenges, and it's a value proposition. Everybody cares about sustainability outwardly, but they're not going to buy anything from you unless they're going to save money, right? And so it's all about value proposition to the customer. And we'll save these guys, depending on who we're talking to, anywhere from 30% to 90% of what they're doing now. And that's hold and haul or anaerobic digestion. So these are the numbers, right? We always have to go through a case study with the customer. What are you paying now? What can we provide? And then look at that comparison. And this happens to be up in Van Nuys, the big brewery up there. And we can save them a good bit of money. And this is just one side stream. They actually produce 90 different brands at that facility in Van Nuys. For chocolate, right? Same thing. Whether they're doing anaerobic digestion or hold and haul, we're saving them significant dollars. And this is what the equipment really looks like. So this is the installation that we had at Joshua Tree. So we had 4 of our BET reactors in hydraulic series. We're treating the brewery waste. It's all PLC integrated, so it's remotely operated. We go up and we'll take water samples to do the analysis and whatnot, but we watch the performance from San Diego. And then from that skid, right, this is on wheels, right, it's like 8 feet by 5 foot by 6 foot, so we can roll that in and plug and play and do a demo on the customer site. And then that translates ultimately into a full scale unit, right, which is what you're seeing there on the right. So that's also going to Joshua Tree this winter. So that's 110 reactors, plus post-treatment systems that we sourced from another company to get us to a point where we can discharge according to Title 22, which governs all water discharge in California. So we have to get from carbon load of 30,000 milligrams per liter down to 30. And we're not going to do that alone. So we have to integrate all the post-treatment technology for that as well. And then the long game, right, is to be able to take these same BET reactors, but have a different form factor that can act for on-site residential sanitation, and get away from these terrible pit latrines, right, to something that can actually enable a flush toilet, safe hand washing water, right, and work off sewer grid and off energy grid. That is the ultimate goal. So as Aquacycl was founded at the end of 2016, we've been gaining some traction both within the San Diego ecosystem and internationally, even winning some awards, and that's been great. We are very excited to move forward. But let me tell you, it ain't easy. This is really what a startup is. Okay, so Ken mentioned the timeline. So I started in 2004 with this particular research, right? And then now we are 2019, so doing the math. It's been a long time getting here, right? On the startup curve, this is 12 years, right? This was the time it took before launch. So our 2016, our launch started here, right? And super excited, we got this, we have a lead investor. We had $1 million committed as a match, and they released $250,000 to us. And so we had to raise another $1 million from other investors before they would release the $750,000, right? And that gives us $2 million to get going. It's like, great, we can do that. What's a pitch deck? Right? So, you know, in the science world, we're used to writing grants and reading grants and writing papers and reading papers and reviewing all of that and speaking very technically, right? That's what we're trained to do. We are not trained to put together P&Ls and pitch decks and all of these things that investors expect to see, and they expect to see a certain format. You need to answer specific questions. The product market fit is the only thing they really care about. They don't care about the product. So that took some time to learn, right? And to be able to communicate. So that's your initial enthusiasm, right? And then when you get to the, oh God, we've got $50,000 in the bank now. We got to lay everybody off and figure out what do we do? Where does this product go? We got to craft the story, and then that's where you really crash, right? And then you start to think and think and think, okay, well, where do we fit? This took us all of 2017 and a good bit of, well, first quarter of 2018, right, to figure that out. Our experimenting and pivoting was not with product, it was with market. Where do we fit? Where can we make money? How can we sell this, right? And then once we understood that and we had demonstrations that were relevant to that story, then investors started coming in. So we were able to meet the goal, right? We raised $2 million by mid-2018, and then we extended our fundraise. We just closed our full round at $4 million, and now I'm raising what's called the Series A, right? More money, because we need to scale. Because as we start talking to more customers, and people are actually now buying things, right? We have revenue, it's starting to work. And right now, we're starting these contract signatures with some very large customers that are going to have exceedingly high expectations, which means we got to raise a lot more money, right? And this is how it scales. And so Aquacycl is just right here, which is exciting and absolutely terrifying, right? So, you know, the investment side of things is a whole other track from grant writing, right? It's you're used to telling a story, and you know there's always the social benefit and the economic benefit to what you're doing, and you have to write that in a grant, right? But it's a very different way of telling that story when you're talking to investors. And so we also had a few things working against us. Okay, Aquacycl, we make hardware, right? Hardware is hard. Everybody knows that. Aquacycl works in water. It's great. But let me tell you, investors hate hardware because it's capital intensive. You're not going to be the next Uber. You're not going to be the next, Spotify. You're never going to be a unicorn because you make hardware, and I hate that word unicorn. It's terrible. So that was tough, right? So okay, we have to first narrow in on investors who are okay with hardware and realize it's going to be a slower growth, right? We're not going to IPO for $1 billion and then lose half of that the next day. But we have to go to the right investor. That's the biggest thing is, okay, understand who you're talking to, what they invest in, and are they going to care to talk to you at all before you set up the meeting, right? So that was learning in 2017. Next thing. Okay, yes, we work in water, and water is the most risk-averse and conservative industry in the world. These are very slow sales cycles. If we were to sell equipment to Hyperion, we could bank on a good 3 years before we go from a conversation to an actual sale installed at their facility. Maybe 1 year, but definitely nothing within the range of months unless there is a catastrophic failure somewhere and they're desperate to make a change, right? Now, it's a long sales cycle for food and beverage customers as well, especially the big multinationals, but they've got bigger problems that they're willing to move faster to solve. Is usually. So another thing when talking to an investor is, okay, well, yes, our sales cycle is long, but here's how we're going to combat that. Okay, so when we're talking to Anheuser-Busch, we're also talking to Joshua Tree Brewery, and he's going to make a decision in 3 months. Anheuser decision is going to come in 9 months, and we can offset our revenue by, both addressing small scale, installations, smaller projects, but faster to close, faster to get money in the door, with the big scale guys, which are ultimately the business makers, right? So we had to figure out how to answer that correctly. And then I'm a woman, if you hadn't noticed. And it is true that there is an unconscious bias, right? For women in science and also women as entrepreneurs. And this bias doesn't just come from men. It comes from men and women equally. And so I'm going to talk a little bit about that. But essentially, right, what I'm talking about here, female founders represent 50% of all startups, okay? But we only receive between 2 and 4% of all venture capital funding. And if you're talking about minority starting a business, right, these numbers are cut in half. 1% of all funding goes to minority founders. And so we need to know this when we walk in the room and start having these conversations, because there's a way to understand the question and reframe it and give it a positive answer back. But these are data from Crunchbase, and this is probably well known, but these little orange bars here, that's female founded company in terms of funding over the years. This is male and female founded together in the pink, and then solely males founded companies in the blue over time. So there really hasn't been a lot of variation, even though there's been more recognition to the issue. So what is unconscious bias? Well, I didn't even realize this was happening in my first few conversations. It had to be pointed out to me. But then once it was, I was like, God, this happens all the time. So an investor to a male entrepreneur. How are you going to succeed? How are you going to be that next, Elon Musk? An investor to a female entrepreneur. How are you going to avoid failing? This is really hard. How are you going to make this happen? Right? And note, I didn't put a gender assignment to the investor, because it doesn't matter if it's a woman or a man asking, more often than not. Right? So what do? Well, you change the conversation. When somebody asks, how am I going to avoid failing? I say, this is how we're going to succeed, right? And you don't call them out for it. You can't be mean or rude about it. But you change the conversation. But we also have to internally change our conversations a little bit. I had to, because the reality is, right, if you're doubting yourself, you're not going to be able to, promote yourself in a way that's going to be exciting and investable, right? And so you have to put that aside. Be like, okay, fuck it. This is going to happen. So that's really what it takes, right? You just have to go for it. And then also, the way that we say things as women often can be phrased a little bit differently to be more assertive, right? So we have to stop apologizing. We have to make sure that we are heard. That the conversation is assertive, right? Not aggressive, but making sure that we don't take a passive role. And I had to really note this in a lot of boardrooms where I'm the only woman, and I had to make sure that I wasn't the only person not speaking. Right. So just some things to keep in mind. And then the other thing that I've had to learn as a CEO and a founder is that Glenn Ross, that movie, is very true. It's very, very real, right? The reality is you always have to be closing, always. So if any of you in this audience have any high-strength wastewater needs, come see me. All right. So with that, I'm happy to answer any questions.
Thank you very much. Interesting talk. I have a question in terms of the operational temperature range. When you think about the adaptability across the globe, in Europe, in cold areas, do you have any range on that?
We do. So we operate within a temperature range of 10 to 55 C, and all of our containers are HVAC enabled, so we can control the temperature remotely.
And have you had ever a challenge of controlling the thickness of the biofilm on your electrode?
Not yet. We thought we would. We see some issues when there's really high protein waste streams. We do see some protein crossover to the outside of the actual cathode. But at the pig farm, where we've been running for 4 years, we do see there's a nice thick biofilm on the cathode, but the efficiencies have not decreased. So we just recently published this, the first year of continuous data at the pig farm with Webb, and so it's available. You can download it, and it really shows the anodic and cathodic potentials across the time under continuous flow, and they're very stable, and they've remained that stable over the course of the last 4 years.
Excellent. And the biggest technical challenge of that? Biggest technical challenge? What was your biggest technical challenge?
To be honest, it wasn't technical.
No.
It really wasn't. I mean, you know. The technology at the time that we launched was at a point where we had already made 10 years of mistakes, right? We had done it with grant money. We've gone through a lot of redesigns, but we didn't do it as a company. So it's been optimization since we launched. But as like the full path, you know, 12-year of development, it was, well, you know, I think we did a lot of trying to recreate the wheel, trying to make a better mousetrap. So we would look at designs and papers and publications and like, okay, oh, this looks great. Maybe if we make this tweak, it'll work better. Ultimately, what we had to do is scrap it and go with, you know, ultimately everything that we learned and what we had failed to do in previous installations and pilot trials and MFC designs, you know, is just not bang our heads against the wall and do that same thing over and over again, but really just, okay, what is going to work based on what we know doesn't work? And it was 12 years of a lot of failure before we got to this point.
I couldn't help when I saw the picture of the toilet at the end. I just watched this Netflix documentary on Bill Gates. Have you heard about the Gates Foundation? They're looking for a toilet like exactly like that in a wastewater treatment. Have you applied for that, or is that sort of out of the realm of what you guys do? It just seems like it fits perfectly.
Yeah. I know. Ever since that Netflix special came out, I've been getting a lot of that. No, it is. It is a great fit, and they've invested a lot of dollars in other groups over the years. Yeah. We are in touch with them. However, they've already picked their pony. They picked their pony back in 2006, and they've invested over $11 million in an MFC group outside in the UK, in Bristol. And they're not committing any more dollars to bioelectrochemical systems in the same way. So while we keep them apprised of what we're doing and how we're doing it, they're not going to be a significant funding resource for us now. Now they're for-profit endeavor, which they started an Accelerator program that kind of spun out of the Gates Foundation work. That's more likely to be a front runner for funding what we do.
And then the other thought was aquaculture. Have you looked into any sort of on-land aquaculture systems? I'm imagining the waste output from those might be, obviously not the aquaculture in the ocean, but the shrimp farms and such. Would that be up the alley?
It works well, but the market opportunity isn't there right now. That'll likely change. But we have done some tests with aquaculture samples. It looks good. Nitrogen is the biggest issue there, and we only remove about 30% of total nitrogen. So we will still require some post-treatment, and the form of nitrogen that comes out of our system is as ammonium, right? So there has to be a removal step before you can recycle.
Just to confirm, so then your product is the electrochemical cells, and then you enrich the microbes that do the wastewater treatment from the wastewater that you flow from the company that you're treating, right?
Correct, yes.
And then, so is there a time frame where at the beginning of the treatment where the water is not being treated as much because you're building biomass slowly at the beginning? And then also, if that's true, do you like rerun that first batch of less well-treated water through the strong biofilm later?
Yes and no. So the startup on site takes about a month.
Okay.
So the fastest startup we've seen is like 2.5 weeks. But over that month, we are processing in batch, right? So we take a load of wastewater, we put in a high diversity of microbes, either sourced from a wastewater plant that's nearby or is already in the wastewater. And then we recycle in batch, but we create different electrochemical environments by how we're controlling current, right? So at the beginning of the enrichment, right, we start off at a really high load. So we're not allowing current to flow. Those electrons are building up, and that forces the biomass to start to form, right, more quickly. Then over operational phases, we look at polarization curves and figure out, okay, well, what would be the optimum resistance at this stage, at this stage, at this stage? So you ultimately drop down the resistor, increase current flow, right, after you see that biofilm is stable. And you know that based on your electrochemical profiles. So that usually takes about a month. Putting that into perspective on other wastewater treatment plants and technologies, that usually takes about 3 to 4 months, right? So it's still fast. Then we go continuous flow.
Okay.
Yeah.
And then what I didn't catch it. What happens to that first month or couple weeks of water that is running through as you're beginning to optimize this?
Well, so we get there, we source their wastewater, we start the enrichment. They keep doing what they've been doing, right?
Okay.
They hold and haul,
Okay.
or they put it in a tank somewhere, right? So we take that volume, we work with it for a month, we put it back into the tank, mix it with all the high concentrate that they've been storing over that month, and then we run it all continuously through.
Okay. Thank you.
Mm-hmm. Yeah.
So you mentioned that you send, so after the primary BAT treatment, it's like you guys consider it as a primary treatment.
Yeah.
But I was wondering after that, do you send your wastewater to some form of secondary treatment, or with some of the plants it goes straight into a discharge body of water?
It totally depends, right, on the customer. So with the site in Tennessee, they have an existing wastewater treatment plant, and then they discharge to sewer from that plant. So what we're doing is we're taking a side stream that they're hauling off site right now, and we're treating that to a point where it can discharge to their existing plant. Right. Then the plant is going to do the rest of the treatment, and then it goes to sewer. In the case of the military, right, what we were actually accomplishing pretty good treatment. It wasn't quite good enough to be called gray water, so it still has to go through some filtration and disinfection prior to being discharged to for reuse, really, discharged to the toilet reflush. If you go through some simple filtration, it could be land applied for irrigation. The system that we have in Tijuana with residential sewage, we are producing irrigation quality water according to WHO standards, not California EPA. So it cannot be used for growing leafy vegetables, but it can be applied to forest land.
Going off of that, so with your operations in Tijuana, what were some, I know you just mentioned the EPA regulations.
Mm-hmm.
Did you run into a lot of other kind of regulatory blocks? Or what were some of those?
Yeah, so some of the regulatory issues and why we are in food and beverage, strategically as well, not just a technology fit, is that we act as industrial pre-treatment in that space, right? So that customer is already permitted to discharge. We just help them stay within that permit. So we don't have to get separately permitted to make that work, right? Now, if we're dealing with human sewage in the United States, that is a whole other ball of wax. The regulatory hurdles for treating on-site, whether you're in a commercial building or just even working with the municipality, become very challenging for a number of reasons, both economic and regulatory. In agriculture, it's a pre-treatment step again. We don't have a lot of permitting issues there, but we do have to deal with the California Air Resources Board, just so that they validate that we're not discharging any, extra sulfides or, GHGs that they're trying to get rid of. for like the MPDS discharge to land, right, it depends on where you are. And this is another issue. So with Joshua Tree, because we are discharging to a seepage pit, we need that post-treatment technology in there, right? We have specific limits we have to hit on average per month for total suspended solid, biological oxygen demand, and total nitrogen, right? Then once we've demonstrated that over about 3 months of operations, then the permit, which is tentatively awarded now, right, will be fully awarded for the County of San Bernardino. But that permit does not get me into the County of San Diego or Napa or Sonoma. I have to go through that process every single county within California. So another reason why being industrial pre-treatment helps a small business is I don't have to go through those hurdles every time.
Okay guys, I think we've kind of run out of time, but I encourage anybody who wants to come and talk to Orianna afterwards. And otherwise we will thank her for her time. Thank you for coming and grab snacks on your way out.